operators for a full-featured um, language. I assume this is your first foray into languages, so I'll cover each concept and line of code. You need to build a complete, usable, fast language implementation. In order to cram two full implementations inside one book without it turning into a doorstop, in order to cram two full implementations inside one book without it turning into a doorstop, this text is lighter on theory than others as we build each piece of the system. I'll introduce the history and concepts. As we build each piece of the system, I'll introduce the history and concepts behind it. I'll try to get you familiar with the lingo so that if you ever find yourself at the cocktail party full of programming language such as you fit in. So apparently they call programming language PL, which is weird because I would have thought that was Premier League.
Exactly.
Um,
And if you had thrown this like on like a group chat or something,
I
I
like
mean,
it, even if they were coders, I thought they
yeah,
were talking about Premier League. Such as you fit in. Yeah, so it's just strange enough. Situation I found myself multiple times. You wouldn't believe how much some of them can drink. We're going mostly, we're mostly going to spend our brain juice getting the language up and running. But this is not to say theory isn't important. Being able to reason precisely and formally about syntax and semantics is a vital skill when working on a language. Okay, yeah, that's true. But personally, I learn best by doing. Same here. It's hard for me to wade through paragraphs full of abstract concepts and really absorb them. But I've coded something. Uh, but if I've coded something, run it and debugged it, then I get it. Um, Static type system in particular require rigorous formal reasoning. Backing on a type system has the same feel as proving a theorem in mathematics. So that's my goal for you. I want you to come away with a solid intuition of how your language lives and breathes. My hope is that when you read other more theoretical books later, the concepts there will firmly stick in your mind. Added, added to this tangible substrate. It turns out this is no coincidence. In the earlier half of last century, Haskell Curry and William Alvin Allwood showed that they are two sides of the same coin. The Curry-Allwood isomorphism. Interesting. That's a nice tip. So while in this stuff, every introduction, uh, every introduction to every compiler book seems to have this section. Um, I don't know what it's about programming languages that causes such existential doubts. I don't think ornithology books were about justifying their existence. So I think ornithology is the study of birds. If I'm not mistaken. Um,
okay.
I worry about justifying their existence. They assume the reader loves birds. Yeah, I was right.
Yeah,
Assume the reader loves birds and starts teaching. Programming languages are a little different. I suppose it's true that the odds of any of us creating a broadly successful general purpose programming language are slim. Designers of the world's widely used languages could fit in a Volkswagen bus. Even without putting the top even without putting the top popped up camper up. If joining an early group was the only reason to learn languages, it would be hard to justify. Fortunately, it isn't. Yeah, these languages are everywhere. For every successful general purpose language, there are 1,000 successful um, niche ones. I used to call them little languages. That's nice. Inflation in the jargon economy led to the name domain specific languages. These are pigeons tailor built to a specific task. They think application scripting languages, template engines, markup formats, and configuration files. Yeah, that makes sense. So like make, XSLT, you're probably seeing like all these weird files somewhere, YAML, Antler, all these like very
with
niche languages
SQL.
that do specific things. Yeah, exactly. Bash, Batch.
Yeah.
I've not used this one. Yeah, of course, this too. This is weird. SCSH, XML, of course. Bison. But there's always like those weird files that have like specific languages that you always have to use in like
Like a
certain
specific
regards.
mm,
Yeah, yeah, like I don't know, like Terraform
basic,
or something.
yeah.
Yeah.
Have like
Hmm.
a configured rules. You just can't you can't just write like any type of thing in JSON.
Yeah,
Yeah.
exactly. Like JSON, yeah, exactly. You're right. So, so they're called domain specific languages. So there are no selection of little languages that you might run into. So it says almost every large software project needs a handful of these. When you can, when you can, it's good to reuse an existing one. instead of rolling your own, of course. So once you factor in documentation, debuggers, editor support, syntax highlighting, and all of the other trappings, doing it yourself becomes a tall order. Yeah, that's true. Um, but there's still a good chance you find yourself needing to whip up a parser or order too. Then there isn't an existing library that fits your needs. Even when you are reusing some existing implementation, you inevitably end up needing um, to debug and maintain it and poke around
Mhm.
in its code, of course. Um, wait, how long is this chapter? Wait, is there a second? Okay, this is next chapter. Okay. So this is chapter one. I'm guessing you read chapter two. So languages are a great exercise. Sure. Long distance runners sometimes train with weights and with weights strapped to their ankles or at high altitudes where the atmosphere is thin. When they later unburden themselves, the new relative ease of light, limbs, yeah, yeah, and oxygen-rich air enables them to run farther and faster. But that's good. Like train your body to like a specific condition and stuff.
Mhm.
Um, so yeah, it says implementing the language is a real test of programming skill. The code is complex and performance critical. You must master recursion, dynamic arrays, trees, and hash tables. So many of the things that I wish I was a master at from TSA. Well, of
Yeah,
course, let's.
and you
You probably
probably
yeah. Go ahead.
yeah, like I saw the next line, like you probably use hash tables at least in your day-to-day
Yeah, day-to-day
programming.
programming.
And
But do you
that's
really understand them?
yeah, exactly.
Yeah, there's like with hash tables, there's like so many things like there's like the hashing function, yeah, like this sort of like randomized um algorithm that generates unique IDs for you, which is
Hmm.
what makes keys in like your hash tables to not be able to clash. Think
Yeah,
like objects in JavaScript or sets, for example. Sets sort of like use half of that algorithm, but they focus more on the key parts, which is why in a set you can't have two keys
damn.
that are the same because exactly. Yeah. It's like they minimize the collision. There's something called collision that they minimize, like the
Mhm.
hashing function. Yeah.
Yeah. So there's like the chance of getting two keys at the same.
Yeah. Yeah, exactly.
Very
But one of them will be very different from the other, or it's just throw an error for you at compile time. Yeah. So you said you probably use hash tables at least in your day-to-day programming, but do you really understand them? Well, after we've crafted our own from scratch, I guarantee you will. So while I intend to show you that an interpreter isn't as daunting as you might believe, implementing one well is still a challenge. Rise to it and you'll come away a stronger programmer and smarter about how you use data structures and algorithms in your day job. Sure. Let's see what you got. One more reason. So this last reason is hard for me to admit because it's so close to my heart. Ever since I learned to program as a kid, of course, I learned to program as a kid. I felt there was something magical about languages. When I first tapped out basic programs, that's the basic language for if you don't know in the audience. Um, one key at a time. I couldn't conceive how basic itself was made. It had
that's
a
like
mixture of awe and terror.
C2
Yeah.
one. I was trying to remember like the course code for that basic
Oh, okay.
CS. Is it
I think it was
one?
CSC 111 FSC something, FSC 113 or something like that. I will
Yeah,
learn basic. Yeah.
exactly.
Yeah. 115 or something. I can't remember. That
I
one key
think
at
it's
a time. I
one.
couldn't conceive.
Yeah,
Yeah.
I think it's one.
Oh, okay. I couldn't conceive how basic itself was made. It had a mixture of awe and terror on my college friends' faces when talking about their compilers class was enough to convince me language hackers were a different breed of human. Sort of wizards granted privileged access to arcane hearts. Um, it's a charming image, but it has a darker side. I didn't feel like a wizard, so I was left thinking I lacked some inborn quality necessary to join the cabal. Though I've been fascinated by languages since I doodled. Right since I doodled.
Oh, so we have a slight break in transmission. So yeah, I think I can use this to give Gregory a shout out. Gregory, thanks for stopping by. Yeah, this actually should be fun, even though we're doing a lot of reading and a lot of learning. But yeah, it's going to be fun, I guess.
Yeah, definitely. So he says, I've been fascinated by languages ever since I doodled made up keywords in my school notebook. It took me decades to muster the courage to truly learn them. That magical quality, that sense of exclusivity, excluded me. Said that its practitioners don't hesitate to play up this image. Two of the seminal texts on programming languages feature a dragon and a wizard on their covers.
Is that like to like scare you before you even start learning
So
the
I think they're
language?
trying to send the message that you must be a god or some sort, or like a wizard to be a
That's great.
programming language. When I finally start cobbling together my own little interpreters, I quickly learned I quickly learned that, of course, there's no magic at all. It's just code, and the people who work on languages are just people. Um, there are a few techniques you don't often encounter outside of languages, and some parts are a little difficult. Um, you don't often encounter outside of languages, and some parts are a little difficult. Yeah, but not more difficult than other obstacles you've overcome. My hope is that you felt is that if you felt intimidated by languages, and this book helps you overcome that fear, maybe I'll leave you just a tiny bit braver than you were before. And who knows, maybe you make the next great language. Someone has to. How the book is organized. This book is broken into three parts. You're reading the first one now. It's a couple of chapters to get you oriented to some of the lingo that language hackers use. Introduce you to locks, the language you'll be implementing. Okay. Each of the other two parts builds um, one complete locks interpreter. Within those parts, each chapter is structured the same way. Chapter takes a single language feature, teaches you the concept behind it, and walks you through an implementation. But that's great. It took a good bit of trial and error on my part, but I managed to carve up the two interpreters into chapter-sized chunks that build on previous chapters, but require nothing from later ones. Yeah, that makes sense. From the very first chapter, you have a working program you can run and play with. With each passing chapter, it grows increasingly full-featured until you eventually have a complete language. Aside from copious, scintillating English prose, chapters have a few delightful facets. Uh, the code. We're about crafting interpreters, so this book contains real code. Every single line of code is included, and each simply tells you where to insert stand in your ever-growing implementation. Many other language books and language implementations use tools like Lex and Yak, so-called compilers that automatically generate some of the source files for an implementation from some high-level description. There are pros and cons to tools like those, and strong opinions. Some might say religious convictions on both sides. So Yak is a tool that takes in a grammar file and produces a source file for a compiler. So it's sort of like a compiler that outputs a compiler, which is where we get the term compiler. So yeah, we will abstain from using them here. I want to ensure there are no dark corners where magic and confusion can hide. So write everything by hand, as you see. It's not as bad as as you see. It's not as bad as it sounds. It means you really won't understand the kind of code that how both interpreters work. So he said Yak wasn't the first of its ilk, which is why it's named Yak, yet another compiler. So a compiler tool is Bison. A similar to is Bison, named as a pun on the pronunciation of yak, like yak. Yeah, I get that.
Oh,
That makes sense. Yeah, like the animal.
but like the full meaning of yak is like yet another. It's
Yet
actually yet
another
another.
compiler. Yeah,
Yeah,
which is funny. Like because YAML is like yet another markup language.
language. Yeah,
Yeah.
that's
So
crazy.
I guess programmers don't have time to name things. So a book has different constraints from the real world. And so the coding style here might not always reflect the best way to write maintainable production software. If I seem a little cavalier about, say, omitting private or declaring a global variable, understand that I do so to keep the code easier on your eyes. The pages here aren't as wide as your ID, and every character counts. So he said also the code doesn't have any comments. That's because each handful of lines is surrounded by several paragraphs of honest to God prose explaining it. While you write a book, when you write a book to accompany your program, you are welcome to omit comments too. Otherwise, you should probably use like this double slash a little more than I do, like comments. You find
Mhm.
all of these self and puns charming and fun. You fit right in here. If not, well, maybe the language nerd sense of humor, then acquired taste. All the book contains every line of code and teaches what each means. It does not describe the machinery needed to compile and run the interpreter. I assume you can slap together a makefile or a project in your IDE of choice in order to get the code to run. Those kinds of instructions get outdated quickly. And I want this book to age like EXO branding, not backyard hooch. I honestly don't get these references, but I'm guessing they're like artists or something.
Shit. Check.
So
Um,
snippets. Um, since the book contains literally every line of code needed for the implementations, snippets are quite precise. Yeah, according to what they said here, literally every line of code needed for the implementations, snippets are quite precise. Also, because I try to keep the program in a runnable state, even when the major features are missing. Sometimes we add temporary code that gets replaced in later snippets. That makes sense. So a snippet with all the bells and whistles looks like this. Defaults, there's a control flow here. So if it's digits, passing an argument, call this number function, else logs or error, something, something. So logs slash scanner.java, in scan token replace one line. That makes sense. Now, why is my um, grandpa going on crazy? So in the center, you have the new code to add. Oh, it makes sense. You have added a few faded out lines above or below to show where it goes in the existing surrounding code. There is also a little blob telling you in which file and where to place the snippet. If that blob says replace lines, there is some existing code between the faded lines that you need to remove and replace with the new snippet. That makes sense. So asides, well, some asides do at least. Most of them are just dumb jokes, amateurish drawings. Let me see. So asides contain biographical sketches, historical background, references to related topics, and suggestion of other areas to explore. So these are the asides. So there's nothing that you need to know in them to understand later parts of the book. So you can skip them if you want. I won't judge you. But it might be a little sad. Let's go back to full screen.
those aside are
Uh,
part of like the key parts as you read along.
yeah, this yeah, this sort of like make it fun, I guess. So just like reading the subtitles as you read the book. So challenges. So each chapter ends with a few exercises. Unlike textbook problem sets, which tend to review material you already covered, these are to help you learn more than what's in the chapter. They force you to step off the guided path and explore on your own. They make you research other languages, figure out how to implement features, or otherwise get you out of your comfort zone. Vanquish the challenges and you come away with a broader understanding and possibly a few bumps and scrapes. Or skip them if you want to stay inside the comfy confines of your tour bus. It's your book. A word of warning, challenges often ask you to make changes to the interpreter you're building. You want to implement this in a copy of your code. The data chapters assume your interpreter is in a pristine, unchallenged state. That makes sense. So design notes. Most programming language books are strictly programming language implementation books. They rarely discuss how one might happen to design the language being implemented. Implementation is fun because it's so precisely defined. We programmers seem to have an affinity for things that are black and white, ones and zeros. I know you love language hackers whose careers are based on this. You slide the language spec under the door with a few months and code and benchmark results come out. Personally, I think the world only needs so many implementations of Fortran 77. At some point, you find yourself designing a new language. Once you start playing that game, and the softer human side of the equation becomes paramount. Things like which features are easy to learn, how to balance innovation and familiarity, which syntax is more readable and to whom. So hopefully your new language doesn't add code assumptions about the weight of a punched card into its grammar. All of that stuff profoundly affects the success of a new language. I want your language to succeed. So in some parts, I end with a design note, a little essay on some corner of the human aspect, programming languages. I'm no expert on this, and I don't know if anyone really is. So take these with a large pinch of salt. That should make them tastier food for thoughts, which is my main aim. Yeah, good preface. I really love this preface. So the
Yeah.
first interpreter, we write our first interpreter JLOX in Java. Focuses on concepts. We write the simplest, cleanest code we can to correctly implement the semantics of the language. This will get us comfortable with the basic techniques and also own our understanding of exactly how the language is supposed to behave. Java is a great language for this. It's a high level. It's high level enough. As I said, the book uses Java and C. Readers ported the language. Readers have ported the language, the code to many other languages. So like it links to like a repo. That's nice. The languages I picked out your bag. Take a look at those. So Java is a great language for this. It's high level enough that we don't get overwhelmed by fiddly implementation details, but it's still but it's still pretty explicit. Unlike in scripting language, there tends to be less complex machinery hiding under a loop, and you've got static types to see what data structures you're working with. That makes sense. I also chose Java specifically because it's an object-oriented programming language. That paradigm swept the programming world in the 90s and is now the dominant way of thinking for millions of programmers. Odds are good you're already used to organizing code into classes and methods, so it'll keep you in that comfort zone. While academic language folks look down on object-oriented languages, the reality is that they're widely used even for language work. TCP and LLVM are written in C++, and most JavaScript virtual machines. Object-oriented languages are ubiquitous, and the tools and compilers for a language are often written in the same language. Yeah, that's really true. Actually, I think TypeScript was written in TypeScript. A compiler compiler reads files in one language, translates them, and outputs in another language. You can implement a compiler in any language, including the same language it compiles. Process called self-hosting. Finally, Java is hugely popular. That means there's a good chance you already know it, so there's less for you to learn to get going in the book. If you aren't that familiar with Java, don't freak out. I try to stick with a familiar, very minimal subset. I use them and put that in Java 7. It's in editors, but that's as far advanced as pictures go. You know that object-oriented language like C or C Sharp or C++, you can model around. Yeah, so you can't compile your compiler using itself yet, but you can have another compiler for your language written in some other language. You use that one to compile your compiler once. Now you can use the compiled version of your compiler to compile future version. What the hell does it say here?
Saying,
And you can discard the original one compiled from the other compiler. This is called bootstrapping. From the image of pulling yourself up by your own bootstraps. Oh, I see. So second interpreter. So in the next part, we'll start all over again. But this time in C. C is the perfect language for understanding how an implementation really goes, all the way down to the Python memory and the code flowing through the CPU. The big reason that using C is so I can show you things in C, particularly things in C particularly is good at. Okay, but does that mean you need to be pretty comfortable with it? You don't have to be the incarnation of Dennis Ritchie, or it should be spooked by pointers. But it shouldn't be spooked by pointers either. If you aren't there yet, pick up an introduction book on C and chew through it, and then come back here when you're done. In return, you come away with this from this book an even stronger C programmer. That's useful given how many language implementations are written in C, Lua, C Python, and Ruby's MRI, to name a few. That makes sense. In our C interpreter, C locks, we are forced to implement for ourselves all the things Java gave us for free. So write our dynamic array and hash tables. We decide how objects are represented in memory and build a garbage collector to reclaim them. I pronounce the name C locks, but you can say it clocks. I say it clocks or even clock, where you pronounce the X like the Greeks do it if it makes you happy. It says our Java implementation was focused on being correct. Now that we have that down, we will turn to also being fast. As interpreter will contain a compiler that translates logs to an efficient bytecode representation. So when I'll get into what that means, which it then executes. So this is the same technique used by implementations of Lua, Python, Ruby, PHP, and many other successful languages. Do you think that this book was just an interpreter book? It's a compiler book as well. Yeah, two for one. Price of one. So we'll even try our hand at benchmarking and optimization. By the end, we have a robust, accurate, fast interpreter for our language, able to keep up with other professional caliber implementations out there. Not bad for one book and a few thousand lines of code. The challenge is there are at least six domain specific languages in the system I cobbled together to write and publish this book. It links to repo. That's very nice. Uh, what are they? So just like challenges to undo. So get the early world program written and run in Java. Set up whatever make files or ID player you need to get working. If you have a debugger, get comfortable with it and step through your program as it runs. I actually need to learn using a debugger in like Visual Studio Code or something like that. VS Code. I'm not very good at like using a debugger to like view the code that's actually running, like stepping through the code. I mostly just like debug by you know, what other
Yeah,
means of debug.
you have like the run and debug button in
Yeah,
VS
there's
Code.
actually what that I can press. Yeah,
Yeah. And you can also see like the output in the terminal
yeah,
while
as the
this.
code. Yeah.
Mhm.
Oh wow, look at the challenges he put here. He said you should go and write a doubly linked list in C. That's nice. So design, what's in the name? One of the hardest challenges in writing this book was coming up with a name for the language to implement. I went through pages of candidate before I found one that worked. I discovered on the first day you start building your own language. Naming is deviously hard. A good name satisfies a few criteria. It's easy to use, of course. Legal and social. It's easy to pronounce. And anything like a couple of syllables or a couple of letters and it's distinct enough to search for. Google language name. Yeah, it doesn't have limited connotation across a number of cultures. The designer of Nimrod ended up renaming his language to name. Customers remember that Bugs Bunny used Nimrod as an insult. Potential name makes it that gauntlet, through that gauntlet. Keep it. Don't get hung up and try to find an appellation that captures the quintessence of your language. The names of the world's other successful language teachers and the name doesn't matter much. All you need is a reasonable unique token. But think about it, come to think of it, it's crazy that nobody ever used Rust because Rust is like a very easy word.
Mhm.
Why did nobody already use Rust?
Like I was going to say, what was it called? We had like JavaScript. I, I think he said when at the time when JavaScript was created, I
Yeah,
mean Java was like a booming language like
yeah,
at that
exactly. Yeah,
yeah.
yeah,
So they named JavaScript just to get that sort of attraction. Like people will be like, oh, is this like a subset of Java or is it
yeah.
related?
Actually,
Yeah, but JavaScript wasn't related to Java. I thought it was like
hmm
different.
not at
Yeah,
all.
exactly. It was like a different stuff. On its own. So naming sometimes can also like
Yeah, be crazy.
come
Yeah,
up.
I agree. I agree. Actually, um. So yeah, chapter two. Let me link you to it. We
Yeah.
made through chapter one, everybody. So we may not be building the compiler today, but there's a high chance we're going to get all the. So we're using code crafters. We set up our repo. We'll start from like building a scanner for our. I think this is like a lexical scanner or something like that. Start
Mm-hmm.
building like our own scanner for our own programs, like sort of one compiler or interpreter or whatever. And we'll work with like parsing, which is where we'll be building our own abstract syntax tree and so many other cool stuff. We may not build the full language, but I'd actually love if we made it to the end of this challenge to like build a fully working language. I will learn so many stuff, honestly. Building a full
Mm-hmm.
language in Rust for that matter. So
So
yeah,
see. Um. Okay. Chapter two. A map of the territory. So you must have a map, no matter how rough. I think this is how we use like hash map. If I'm not wrong. So you must, no matter how rough, otherwise you wander all over the place. In Lord of the Rings, I never made anyone go farther than it could on a given day. J.R.R. Tolkien. Okay. Uh, we don't want to wander all over the place. So before we set off, let's scan the territory charted by previous language implementers. Um, it will help us understand where we're going, and the alternate route others have taken. So first, let's establish a shorthand. Must this book, uh, much of this book is about a language implementation, which is distinct from the language itself in some sort of Platonic ideal form. Things like stack, bytecode, and recursive descent are not and both one particular implementation might use. From the user's perspective, as long as the resulting contraption faithfully follows the language specification, it's all implementation detail. And we're going to spend a lot of time on those details. So if I have to write language implementation every single time I mention them, I'll wear my fingers off. So instead, I'll use language to
Yeah.
refer to any language or implementation of it. Okay, makes sense. Or both, unless the distinction matters. Yeah. So back to the language. Engineers have been building programming language since the dark ages of computing. As soon as we could talk to computers, we discovered doing so was too hard, and we enlisted their help. I found it fascinating that even though today's machines are literally a million times faster, and have others in magnitude more storage, others of magnitude more storage, the way we build programming language is virtually unchanged. So, though the area explored by language designers is vast, the trail are carved through the trial they've carved through it a few. Not every language takes the exact same path. Some take a shortcut or two, but otherwise they are reassuringly similar. From Rear Admiral Grace first combo. What's combo? Combo compiler.
It was built by Grace Hopper. I think she was the
Yeah,
first ever programmer. Um, yeah, the first
all
ever
the way
programmer or something.
all the way to this
Maybe
to
that was
some
Adam.
to some hot new transpiled to JavaScript language whose documentation consists entirely of a single poorly edited readme in Git repository somewhere. That's crazy. So there are certainly dead ends, sadly, to um, code sacks of CS papers with zero citation and now forgotten optimization that only made sense when memory was measured in individual bytes. This is
Yeah,
taking
actually.
at some set of people, you know. So I virtualized the network of paths and interpretation implementation may choose as climbing a mountain. You start off at the bottom with the program as raw source text, literally just a string of characters. Each phase analyzes the program and transforms it to some higher level representation where the semantics, what the authors want the computer to do, become more apparent. So eventually, we reach the peak. We have the bird's eye view of the user's program and can see their code, see what their code means. We begin our descent down the other side of the mountain. We transform this highest level representation down to successively lower level forms to get closer and closer to something we know how to make the CPU actually execute. Okay, so this is like the representation of all you have been explaining. So you have scanning tokens, passing syntax tree, okay, analysis, optimization, and then it goes down. So you have the source code and high level language.
Hmm?
So true work,
So like
interpretation. Mm-hmm.
source code, high level language, byte code, then your machine code.
Yeah.
Oh wait, am I tripping? Yeah.
So optimization, it optimizes intermediate representation, code generation, and then goes back to machine code. Let's trace through each of these trials and points of interest. Our journey begins on the left, yeah, with the bare text of user stuff, source code. So we have a bunch of var average. Okay,
So you
so
declare the variable.
yeah, so var average equal to min plus max slash two. Yeah. So let's see, scanning. So the first step is scanning, also known as lexing, or if you are trying to impress someone, lexical analysis. They all mean pretty much the same thing. I like Lexing because it sounds like something an evil civilian would do. But I'll use Scan because it seems to be marginally more
Come on,
commonplace.
please. Mm-hmm.
So a scanner or a text takes in a linear stream of characters and chunks them together into a series of something more akin to words. In
Mm-hmm.
programming languages, each of the words is called a token. Okay, some tokens are single character like these parentheses, and others may be several characters long, like numbers 1 to 3, string literals, and identifiers main. So lexical comes from the Greek word. Okay, from the Greek root lex, meaning word. Oh, makes sense. I remember this lexical when we used to do English grammar back in like
Yeah,
yeah,
yeah.
this lexical something. So some characters in the source file don't actually mean anything. White space is often insignificant, and comments by definition are ignored by the language. So the scanner usually discards this, leaving a clean sequence of meaningful tokens. So it makes sense. So when the scanner goes through, it takes off like what's it called, white spaces and
Mm-hmm.
comments like that the language doesn't actually need, basically. So it
Yeah,
just leaves you with only the meaningful stuff. So var,
yeah.
average, assignment operator equals to this min plus max, then slash two. So the next step is passing. Next step is passing. This is where our syntax gets a grammar. The ability to compose larger expressions and statements out of smaller parts. Do you ever did you ever diagram sentences in English class? Okay, if
Nope.
so,
Having
you've
in the
done
wrong English class.
yeah. So if so, you've done what a parser does. Except that English has thousands and thousands of keywords and overflowing cornucopia of ambiguity. So programming languages are much simpler. Uh, okay. A parser takes the flat sequence of tokens and builds a tree structure that mirrors the nexted nature of the grammar. These trees have a couple of different names. You have the parse tree or the abstract syntax tree. I think we've seen this before. Depending on how close
Yeah.
the syn- syntactic structure of the source language are, they are. So in practice, language hackers usually call them syntax tree or ASTs, or
Mm.
often just trees. Um, so this is how it's going to look when this next step is being run. So you have average, okay, variable, expression binary, which is your I think for
Yeah, that
division.
variable.
Yeah.
Variable. They are breaking down the variable now. Yeah, the variable declaration. Yeah.
So we have literal two, variable min and max.
I think the way
Okay.
it works is that you take, like from what I remember, you always have to take the expression. Like for example, like they are operators and operands in like mathematics and
Yeah.
stuff. So
Mm-hmm.
so
So
now
these
for all
ones
this
are
division, yeah, the operators are always the what am I? Yeah, which one is operands? Operands is like normal variables now, or maybe
yeah. The
constant. Yeah,
operator
so you
is
have to take your yeah.
yeah.
So you have to connect them by operator. So now, for example, the thing that connects min and max and two is division. So you have to put division at the top. Then you move on to the next operator, but if two will be on the right hand side. Then you now use plus to connect min and max or something like that. I think that's the way it works. But average is the variable itself, so you just bring
Yeah,
from
because you
average.
have
Yeah,
what connects min and max directly is this plus,
yeah,
right?
exactly.
What
And
connects
division,
min and max is this division,
exactly. Yeah,
and then average is like the actual what's
variable
called
declaration.
yeah.
Yeah,
So that makes sense. So passing has a long, rich history in computer science that is closely tied to the artificial intelligence community. Many of the techniques used today to pass programming languages programming language were originally conceived to pass human languages by AI
Mm.
researchers who are trying to get computers to talk like us. That's
Oh, that's
crazy.
nice. That's a fun
Yeah.
realization.
hmm And till today, I think that AI researchers are
They're
still
still doing that. Yeah.
trying to get AI to like act like humans. I
Hmm.
mean, one day, maybe one day we'll get to that point, but for now,
Yeah.
we're still very far from it. Although we made
I
huge
mean, we're
progress.
close though. We're close
Yeah.
though. They now like compute like AI can now understand languages. I think, for example, a fun project to even do could be like making an AI compiler, like having AI be a compiler for your language. It could actually be a fun project to work on because AI can understand most things now, and it can use other information to give responses. But there's still the like thing of like fine tuning and hallucination and stuff though. So maybe
Yeah.
it could not be as
I
accurate
guess
as.
yeah, no, I think it's something doable. You just have to be like uh maybe like doing like a way to like maintain
Yeah,
the code generated by the AI. So because you have
yeah,
some things
exactly.
get updated and all that type of thing. But it's
Mhm. Yeah,
certainly like with what AI is doing now, I don't think um that would be like a far stretch for AI
yeah,
to do.
exactly. To do that, yeah.
Elon Musk has
Hmm?
this robot AI that could even relate to humans. Like
What's that?
there's this robot that
Oh wow, that's the
I think was it Tesla, yeah, they released like last
interesting.
year. Yeah.
Wow, crazy stuff.
Mhm. So it turns out human languages were too messy for the rigid grammars those parsers could handle. But they were a perfect fit for the simpler artificial grammars of programming languages. Alas, we flawed humans still manage to use those grammar. They still manage to use those simple grammars incorrectly. So the parser's job also includes letting us know when they do it by reporting syntax error. So it's like they said a set of okay, this is how you should write things, and then you're not trying to come and do it the opposite thing. So that's what brings about syntax error, trying to write something that's not even correct or something. It's not in the dictionary. So static analysis. The first two stages are pretty similar across all implementations. Now, the individual characteristics of each language start coming into play. At this point, we know the syntactic structure of the code. Things which are expressions are nested in each, but we don't know much more than that. So in an expression like A plus B, we know we're adding A and B, but we don't know what those names refer to. Okay. Are they local variables, global? What are they
Mm-hmm.
defined?
Yeah.
So the first bit of analysis that most languages do is called binding or resolution. For each identifier, we'll find out where the name is identified and wire the two together. This is where
Mm-hmm.
scope comes into play. The region of source code where a certain name can be used to refer to
25.
certain declaration.
Yeah.
This means so
And this
if
was a
a
great realization for me when I was learning to code. So when I learned JavaScript that time, most of the
Mhm,
concept I learned from there, I thought they were specific to only JavaScript. Until I started like looking at other languages, and I started realizing that all the concepts were like they were just building towards a common goal, but with like
mhm,
different ways.
yeah,
I guess that's what programming languages are. Because in the end, all of them still compile to like bytecode. They run on one machine somewhere, and they still sort of get you what you need. I think at the point of execution, programming language used to achieve it is always irrelevant because the only places programming language matters is in like to the like dev computer. That's when it matters. But after that stage, it's irrelevant because nobody cares what you used to write the code. It's just like the sort of machine code or something like that that executes stuff. Yeah.
I think you're right, and I think the whole purpose of having like um, higher level languages is to bridge that gap of having
Yeah,
to
to
put in.
speak with the machine.
Exactly. So
Yeah,
basically, they are taking those commands and those things, they are putting it in simpler
keywords.
terms. Exactly,
Yeah,
keywords are understandable. So most times when you see, if you see if, right, it's the condition. Like some things are
yeah,
just meant exactly. So it's not like they want to. I mean, I know of people like what we saw in like the introduction, an example
yeah,
of where he said they had like a dragon and stuff on the book. So imagine people have, oh, yeah, imagine people have to say, oh, now I want to do this programming language, but I want it
yeah,
to be that with only some certain set of people. So they now
yeah,
go and make
exactly.
syntax that are not
Mm.
even, I don't know, they don't even match exactly. They are trying to
Yeah,
make so if someone reads your code, you'll be like, oh, what's this guy even writing?
this guy is a god.
Yeah, what is this guy?
This
So
guy is
I
a
think
genius.
exactly that the it beats the purpose of having high level language.
Yeah,
So if you want to
yeah.
write jargons that are not relatable, go and write machine compiler. Go and write
It's
assembly.
binary.
Exactly, go and write binary. And that one you know that you're dealing with. But when you want to do a higher level language and you want to start, it just
Yeah,
defeats the entire purpose. So if the language is statically typed, that is when we type check. Once we know where A and B are declared, we can also figure out their types. And if those types don't support being added to each other, we report a type error. Okay, the
yeah.
language we read in this book is a dynamically typed. It's dynamically typed, so it will do its type checking later at runtime or
At runtime. Yeah. So we are building like JavaScript, I guess.
JavaScript here.
Yeah.
So if it was a compile time, to be like TypeScript. So
Hmm.
once you write immediately, just
Yeah.
back at it.
Throws the error. Yeah. TypeScript will
Mhm.
scream at you instantly.
So take a deep breath. We have attained the summit of the mountain and a sweeping view of the user's program. All this semantic insight that is visible to us from analysis needs to be stored somewhere. Okay, there are a few places we can squirrel it away. Often, often it gets stored right back as attribute on syntax tree itself. Extra fields in the node that aren't initialized during passing but get filled in later.
Hmm.
Other times, we may store data in a lookup table off the side. Typically, the
Yeah.
keys to this table are identifiers, names of variables, and declarations. In
Yeah.
that case, we call it a symbol table, and the values it associates with each key tells us what that identifier
Refers to,
refers.
yeah.
Okay, these are
Yeah.
like this one is like the one I'm used to, like the variable, um, like storing a variable. So we
Yeah.
just have the key to access that variable. The most
Yeah.
powerful
Exactly.
bookkeeping is to transform the tree into an entirely new data structure that more directly expresses the semantics of the code. That's the next section. Okay.
Mhm.
Everything up to this point is considered the front end of the implementation. You might guess
Yes.
everything after this is the back end, but no. Back in the days of John, when and back end were coined, compilers were much simpler. Later, researchers invented new faces to stuff between the two apps, or rather than discard the old term, William Wolf and company lumped those new faces into the charming but spardy
Especially,
paradoxical.
especially paradoxical.
Wait, is this middle end like um
Yeah, it's a thing. Middle end is like where you have like intermediate code generations. So like the syntax tree you've gotten from the front end, you pass it directly to the middle end, and you sort of like make some, I think, some references or something, and then you
before
generate this. Yeah, I think it generates this intermediate sign code thingy that you can then pass on to like the back end to get object code or something like that.
this is new. So intermediate representation. You can think of the compiler as the pipeline where each stage job is to analyze, organize the data, representing the user's code in a way that makes the next simpler to implement. The front end of the pipeline is specific to the source code, source language, and the program is written in. The back end is concerned with the final architecture where the program will run. In the middle, the code may be stored in some intermediate representation IR that isn't tightly tied to either the source or destination forms, hence intermediates. So instead the IR acts as interface between these two languages. And there are a few well-established styles of IR. Hit your search engine's choice and look for control flow graph, static single assignment, continuous pattern style, and three address code.
The address code. Yeah.
Uh, at this, we let me take
So, sorry.
control flow graph. Let's see. So a control flow graph is a graph that shows all the paths a program can take while running. So it's
Yeah.
the directed graph, meaning the order of nodes matter. Yes. So it shows nodes, um, which is represent the control flow paths between basic nodes. Helps clarify data flow and control flow issues. Can be used to detect malware. Okay, makes sense.
Interesting.
So it's mostly used in static analysis as well as compiler application. Okay, as they accurately represent the flow in program units.
Side the programming. Yeah.
There used to be this um the control. Yeah, I
What's
think it's
that?
control. This chart, something similar like this, just made me remember the
Flowcharts.
control flow chart here. Yeah,
Yeah. Yeah.
something
No,
like
no.
that.
Flowcharts are like limited in logic. Flowcharts are mostly like um decision based, I guess, process based. So like you
Mm-hmm.
can basically represent any process, I guess, with a flowchart.
Yeah, exactly. So it's like
Wow, very good.
I think they use flow chart in like engineering, general engineering.
Yeah, because it's very like
Hmm.
it's multi focused, I guess. You can use it for anything.
Yeah. So this lets you support multiple source language and target platform that with less effort. Say you want to implement Pascal, C, and Fortran compilers, and you want to target x86, ARM, I don't know, Spark. Normally, that means you are signing up to write 9 full compilers, Pascal, x86, CARM, and every other combination. I shared a shared intermediate representation reduces that dramatically. You write one front end for each source language that produce the IR, then one backend for each target architecture. Now you can mix and match those to get every combination. If you've ever wondered how GCC supports so many crazy languages and architectures like Model 3 on Motorola IRs, mainly Gimpool and RTL. Target backends like the one for city state key, then take those IRs and produce native code. Okay. There's another big reason we want semantics more apparent. So this is the next step, optimization. So once you understand what the user's program means, we are free to swap it out with different program that has the same semantics but implement them more efficiently. We can optimize it. So a simple example is constant folding. If some expression always ever use the point 0.75 divided by 2 times 0.75 divided by 2. Okay, we could do all that arithmetic in the compiler and change the code to penny area 0 points. Will make sense. So instead of doing this at runtime,
Yeah.
so we do it
Hmm.
compiled and get
Yeah.
value, just a single value for penny area. So that
Yeah.
when yeah, this makes sense. So that when you get to runtime, you just have a value. But what if this value was dynamic though?
Yeah. I mean, in the end, you still have to have for every specific operations, they will still have to have a constant value, even though they are dynamic, depending on what value you pass. So there's always going to be a variation. It's
Mm-hmm.
just going to
Yeah.
be like a case of different variations of the same operation.
Mm-hmm.
Yeah.
So optimization is a huge part of the programming language business. Many language hackers spend their entire careers here, squeezing every drop of performance they can out of their compilers to get their benchmark a fraction of a percent faster. It can become sort of it
Session.
can become a sort of obsession. So we are mostly going to hop over the rabbit hole of this book. Many successful languages have surprisingly few compile time optimization. For example, Lua and C Python generate relatively unoptimized code and focus most of their performance effort on the runtime. Okay, so it's like a two-way thing. So if you can't
Hmm.
resist poking your feet into the hole, some keywords you get to get you started are constant propagation, common sub expression, loop invariant
Yeah.
code motion, global value numbering, strength reduction, scalar replacement of aggregates, dead code elimination, and loop unrolling. So code generation, I think this is the last uh,
Awesome.
step. So we have applied all the optimization we can think of to the user's program. The last step is converting it to a form the machine can actually run. In other words, generating code or code gen, where code here usually refers to the kind of primitive assembly like instruction a CPU runs and not the kind of source code a human might want to read. So finally, we are in the back end, descending the other side of the mountain. From here on out, our representation of the code becomes more and more primitive, like evolution run in reverse. As we get closer to something our simple-minded machine can understand. So we have a decision to make. Do we generate instruction for a real CPU or a virtual one? If we generate real machine code, we get an executable that the OS can load directly into the chip. Making code is lightning fast, but generating it is a lot of work. Today's
Yeah.
architecture has piles of instruction, complex pipelines, and enough historical baggage to fill a 747's luggage bay. Uh, for example, the AAD async adjust
ASCII.
AX bit prediction. Yeah, ASCII. Instruction lets you perform division. Okay, which sounds useful, except the instruction takes as operands two binary coded decimal digits packed into a single 16-bit register. When was the last time
What?
you needed BCD on a 16-bit machine?
That's weird. So you're using like BCDs to like interpret the values you pass in. That's like a lot
Exactly.
of work, honestly.
A lot of work.
And
Um,
BCDs are always like 16 bits, from what I remember.
mhm. So speaking Speaking the chip's language also means your compiler is tied to a specific architecture. If your compiler targets x86 machine code, it's not going to run on an ARM.
Yeah,
All the
yeah,
way back to the 60s, during the Cambrian explosion of computer architectures, the lack of portability was a real obstacle. To get around that, hackers like Martin Richards and Nicholas Waits of BCPL and Pascal fame respectively made their compilers produce virtual machines code instead. Okay, instead of instructions for some real chip, they produce code for a hypothetical idealized machine. We would call this P code for portable, but today we generally call it bit code because each instruction is often a single bit long. So these syntactic instructions are designed to map a little more closely to the language semantics and not to be so tied to the peculiarities of any one computer architecture and it's accumulated historical craft. You can think of it like a dense binary encoding of language low level operations. Okay.
mhm.
So this is instead of trying to uh, do like native code
Yeah.
for
They just
each.
device code.
Uh,
Yeah,
so the basic
but that's why
principle here is
most programming languages have virtual machines, which I think you'll be going into next, because that virtual machine allows it such that you can run that code on any platform as long as you have the VM on it.
yeah. So the basic principle here is that the further down the pipeline you push the architecture specific work, the more earlier phases you can share across architectures. So virtual machines. So if your compiler produces bit code, your work isn't over once that's done. Since there is no chip that speaks that bit code, it's your job to translate. Again, you have two options. You can write a little mini compiler for each target architecture that converts the bytecode to native code for that machine. You still have to do work for each chip you support. But this last stage is pretty simple and you get to reuse the rest of the compiler pipeline across all the machines you support. You're basically using your bytecode to as an intermediate
It's an
representation.
intermediate. Yeah.
Uh, there's a tension though. Many optimization like register allocation and instruction selection work best when they know the strengths and capabilities of the specific chip. Figuring out which parts of your compiler can be shared and which should be target specific is an art.
Mm-hmm. Mm-hmm.
A lot of details that you need to
Yeah. Pay
um,
attention to.
yeah. So, or you can write a virtual machine, a VM, a program that emulates a hypothetical chip supporting a virtual architecture at runtime. Running bitcode in a VM is slower than translating it to a native code ahead of
Yep.
time because
True.
every instruction must be simulated at runtime each time it executes. In return, you get simplicity and portability. Implement your VM in space C, and you can run a language on any platform that has a C compiler.
I see compiler. Yeah.
So this is how the second interpreter we build in this book works. So the term virtual machine also refers to a different kind of abstraction. A system virtual machine emulates an entire hardware platform, an operating system and software. And this is how you can play Windows games on your
Your
Linux
Linux
machine
machine.
and how cloud providers give customers the user experience of controlling their own server without needing to
Server in
physically
quotes.
separate separate computers for each user. The kind of VM we'll talk about in this book are language virtual machines or process virtual machines if you want to be unambiguous.
And
Um so runtime with this chapter too is
damn, this
quite
chapter is long.
yeah.
Are we going to finish this though today? We can take a break here if you want.
Nah,
We only have like
it's
one more chapter to go.
mhm. I mean, if we can finish the three chapters this week, I mean, this
No,
like
no, I don't think it's worth it to do the third chapter right now. We should do the third chapter together with chapter four because chapter four is where scanning starts. We'll keep our memory fresh because if we start writing the code, and by next week we still have to reference the book again. But by next week, if we start with chapter three, we still have like a fresh memory, and then we just dive straight into code.
yeah. But this is like a lot of information. On like this book is
Yeah,
actually
yeah.
very deep.
We still have to come back to reference it anyways. That's why
Mhm.
I'm still kind of skeptical of reading the entire thing. Yeah.
So yeah. So runtime, we have finally hammered the user's program into a form that we can execute. The last step is running it. If we compile it to machine code, we simply tell the operating system to load the executable and off it goes. If we compile it to bit code, we need to start up the VM and load the program into that. In both cases, for all but the basis of the low level language, we usually need some services our language provides while the program is running. For example, if the language automatically manages memory, we need a garbage collector going in order to reclaim unused bits. If our language supports instance of um, tests so you can see what kind of objects you have, then we need some representation to keep track of the type of each object during execution. All this stuff is going at runtime, so it's called appropriately the runtime. In a fully compiled language, the code implementing the runtime gets inserted directly into the resulting executable. In say Go, okay, each compiled application has its own copy of Go's runtime directly embedded in it. If the language is run inside an interpreter or peer, then the runtime lives there. This is how most implementation of languages like Java, Python, and JavaScript work. Hmm.
Mm-hmm.
So shortcuts and alternate routes. That's a long path covering every possible phase you might implement. Many languages do work the entire route, but there are a few shortcuts and alternate paths. So we have single pass compilers. Some simple compilers interleave passing, analysis, and code generation so that they could produce output code directly in the parser without ever allocating any syntax trees or other IRs. These single pass compilers restrict the design of the language. You have no intermediate data structure to store global information about the program, and you don't revisit any previously passed part of the code. That means as soon as you see some expression, you need to know enough to correctly compile it. Pascal and C were designed around this limitation. At the time, memory was so precious that a compiler might not even be able to hold an entire source file in memory,
Mm.
much less the
Yeah.
whole. This is why Pascal's grammar requires type declaration to appear first in a block. It's why in C you can't call a function above the code that defines it. Or
Yeah, that
when
makes sense.
unless you have an explicit forward declaration that tells the compiler what it needs to know to generate code for all call to the later function. I think in JavaScript, it's what we call like hoisting, like where
Yeah.
you can even before,
Yeah. Exactly.
yeah, even before declaring it. So syntax
Hmm?
directed translation is a structured technique for building these all at once compilers. You associate an action with each piece of grammar, usually one that generates output code. Then, whenever the parser matches the chunk of syntax, it executes the action, building up the target code one row at a time. So we have tree work interpreters. Some programming languages begin executing code right after passing it to an AST with maybe a bit of syntax analysis applied. static analysis
static
applied.
analysis.
To run the program, the interpreter traverses the scene with one branch and leaf at a time, evaluating each node that is as it goes. Okay, this implementation style is common for student projects and little languages, but it is not widely used for general purpose languages since it tends to be slow. Some people use interpreter to mean only those kinds of implementation. The other defines the word more generally. So I'll use the inarguable explicit true work interpreter to refer to those. Our first
Yeah.
interpreter to a notable exception in the early versions of Ruby, which were tree workers at 1.9, the canonical implementation of Ruby switched from the original MRI Mat Ruby interpreter to Koichi Sada's you have yet another Ruby VM. Why did they like this yet another? Yet,
I mean, if you think about it, it's yet another one. So why didn't you
yeah,
just give it the name?
at this point, whenever I now see anything that has YA prefixed before my head just goes to yet another. It's a bit code virtual machine. So transpilers, okay, writing a complete backend for a language can be a lot of work if you have some existing generic IR to target. You could bolt your front end onto that, otherwise, it seems like you're stuck. But if you treated some other source language as if it were an intermediate representation, so the first transcompiler XLT86 translated 8080 assembly into 8086 assembly. Hmm. That might seem straightforward, but keep in mind that the 8080 was an 8-bit chip and the 8086 is a 16-bit chip that could use each register as a pair of 8-bit ones. XLT 86 did data flow analysis to track register usage in the source program and then efficiently map it to the register set of the 8086. These are like um, early low level stuff. So uh, you write a front end of your language, and in the back end, instead of doing all the work to lower the semantics to some primitive target language, you produce a string of valid source code for some other language that's about as high as yours. Then use the existing compilation tools for that language as your escape route off the mountain and down to something you can execute. They used to call this a source to source compiler or a transcompiler. After the rise of languages that compile to JavaScript in order to run in the browser, they've affected the hipster software compiler. So it was written by it was written by Gary Kinder, a tragic hero of computer science. If there were ever ones, okay. One of the
Yeah,
first
I think
people to
back to
recognize
the.
it.
I think this transpilers thing is what TypeScript uses as well.
Mm-hmm.
They basically just take JavaScript and they probably just took we when they
Yeah,
got to
even,
the intermediate
even
representation, they just
what you
took
call
what JavaScript already did.
yeah, even when you have I think when you write like Python,
Mm,
when you write Python front end,
yeah,
it transpires because I've seen a use case when they use like Python to write like front end stuff, like what JavaScript is supposed to do.
yeah,
So it
yeah,
transpires JavaScript first for it to be like be able to be rendered on the browser, something like that.
yeah. I mean that makes sense because only JS runs on the web. Only JS runs on the front end rather. So you still sort of need a means to eventually convert it back. I think PHP runs on the web too, but I'm not sure if it's purely PHP that runs on the web. Guessing some parts of it would also have to be JavaScript for it to run well.
Hmm. one of the first people to recognize the promise of microcomputers. He created PL/ML and CP/M, the first high-level language and OS for them. They used to call it a source. Okay, looked at this. So while the first compiler translated one assembly language to another, today most transpilers work on higher level languages. After the viral spread of the Unix to machines, various and sundry, there began a long tradition of compilers that produced C as their output language. C compilers were available everywhere. Unix was and produced efficient code. So targeting C was a good way to get your language running on a lot of architectures. So web browsers are the machines of today, and their machine code is JavaScript. So these days, it seems almost every language out there has a compiler that targets JS, since that's the new way to get your code running in the browser. Exactly. So JS used to be the only way to execute code in a browser. Thanks to
Now it's
WebAssembly,
Watson.
compiler second
Yeah,
lower level language that can target that runs on the web. Oh, this WebAssembly.
Watson. Yeah, Watson.
Yeah.
Watson is like the new. That seems like one of the newer standards right now that you can use to run front end on the web. So you don't
Mm-hmm.
essentially need to get to
Yes.
JavaScript. Yeah.
Mm-hmm. Nice. So the front end scanner and parser of a transpiler looks like other compilers. They need the source language with only a simple syntactic scheme over the target language. You may skip analysis entirely and go straight to outputting the analogous syntax in the destination language. If the two languages were more semantically different, you will see more of the typical phases of a full compiler, including analysis and possibly even optimization. Then when it comes to code generation, instead of outputting some binary language like machine code, you produce a string of grammatically correct source, well, destination code in a target language. So either way, you run the resulting code through the output language existing compilation pipeline, and you are good to go.
Hmm.
Mm. So just in time compilation. This last one is less a shortcut and more dangerous. Fine,
Alpine.
best reserved for experts. So it means that if you are not really good and you try to use it, it could easily turn to something else. So the fastest way to execute code is by compiling it to machine code. But you might not know what architecture your end users machine support, what to do. So you can do the same thing, the hotspot Java VM virtual machine, Microsoft Common Language Runtime, and most JavaScript interpreters do. On the end user's machine, when the program is loaded, either from the source, in the case of JS, or platform independent bytecode for the JVM and CLR, you compile it to a native code for the architecture of their computer support. So naturally, it's called just-in-time compilation. Most hackers just JIT, pronounced like it rhymes with fit, or JIT. The most sophisticated JITs insert profiling hooks into the generated code to see which regions are most performance critical and what kind of data is flowing through them. Then over time, they will automatically recompile those hotspots with more advanced optimizations. This is a course exactly where the hotspot. This is of course exactly where the hotspot JVM gets its name. So you have compilers and interpreters. Now that I've stuffed your head with a dictionary's worth of programming language jargon, finally address a question that coders since time. in memorial. What's the difference between a compiler and an interpreter? So let's see. So it turns out
Okay.
this is like asking the difference between a fruit and a vegetable. Seems like a binary, like a binary either or choice. But actually, fruit is a botanical term and vegetable is culinary. One does not strictly imply the negation of the other. There are fruits that aren't vegetables, right? Like apples, and vegetables that aren't fruits, like carrots. But also, edible
Because
plants are both fruits and vegetables, like tomatoes. This is revealing though. Carrots.
yeah,
Carrots
yeah.
are vegetables, okay, but they are not fruits. Makes
I
sense.
mean, nobody calls them fruits though, so it's kind of
Yeah, exactly. I mean, these are things that I mean you know them, but like you only get to think about them when you see something like this. You start thinking.
yeah, exactly.
So peanuts, which are not even nuts, and cereal, like wheat, are actually fruits. But I got this drawing wrong. What can I say? I'm a software engineer, not a botanist. I should probably erase the little peanut guy, but it's so cute that I can't beat this guy holding the leaf. Now, pine nuts, on the other hand, are plant-based food that are neither fruits nor vegetables, at least as far as I can tell. This is pine nut outside. So back to languages. So compiling is an implementation technique that involves translating a source language to some other, usually lower level form. So compiling is an implementation technique, right, that involves translating the source language, okay, to
Mhm.
some other lower level form. When you generate bit code or machine code, you are compiling. When you transpile to another high level language, you are compiling to. Hmm.
Hmm. Okay.
When we say language implementation is a compiler, we mean it translates source code to another form but doesn't execute it. Okay, a language implementation is a compiler. The user has to take the resulting output and run it. No, okay. Conversely, when we say an implementation is an interpreter, we mean it takes in a source code and executes it immediately. It runs program from source. Mm. Takes a source code and executes it immediately. Okay. So like apples and oranges, some implementations are clearly compilers and not interpreters. GCC and Clang take your C code and compile it to machine code. An end user runs that executable directly and may never know which tool was used to compile it. So those are compilers for C. In older versions of Math's canonical implementation of Ruby, the user ran Ruby from source. The implementation passed it and executed it directly by traversing the syntax tree. No other translation occurred, either internally or in any user visible form. So this was definitely an interpreter for Ruby.
Yeah.
Okay, that makes sense. But what of C Python? When you run your Python program using it, the code is passed and converted to an internal bitcode format, which is then executed using the VM. From the user's perspective, this is clearly an interpreter. They run their program from source. But if you look under CPython's Kali skin, you see that there is definitely some compiling going on. The answer is the answer is that it is both. CPython is an interpreter and it has a compiler. In practice, most scripting languages work this way, as you can see. Mm. So we have compiler, TypeScript, Java, CoffeeScript, Rust, Clang, and interpreter we have PHP. The go-to is even more horticultural curiosity. If you run go build, it compiles your Go source code to machine code and stops. If you type go run, it does that, immediately executes the generated executable. So Go is a compiler. So you can use it as a tool to compile code without running it. As an interpreter, if you can invoke to it immediately, run a program from source. And also as a compiler, when you use it as an interpreter, it is still compiling internal. Mm, makes sense. So if you're able to run if you're able to
Like
run
I
the
learned a lot. I've learned a
yeah,
lot from just reading this book right now.
exactly. So if you're able to run it immediately,
Mm-hmm,
right, that you could like tap into the source directly, then
mm-hmm.
it's an interpreter. But still, sometimes an interpreter might need like to do some
Some
compiling.
compilations, yeah. Mm.
So that overlapping region in the center is where our second interpreter lives to, since it internally compiles to byte code. So while this book is nominally about interpreters, we'll cover some compilations too.
Compilation too. Okay.
Um, so our journey, that's a lot to take in all at once. Don't worry. This isn't the chapter where you are expected to understand all of these pieces and parts. I just want you to know that they are out there and roughly how they fit together. So this map should serve as to serve you well as you explore the territory beyond the guided paths we take in this book. I want to leave you yearning to strike
Yearning.
out your own and wander all over that mountain. So, but for now, it's time for your own journey to begin. Tighten your bootlaces, cinch up your pack, and come along. From here on out, all you need to focus on is the path in front of you. Henceforth, I promise to tone down the whole mountain metaphor thing. Fun. So challenges we have a couple.
These are fun challenge. These are fun challenges though.
Mhm. Pick an open source implementation of a language you like. Download the source code and poke around it. Try to find the code that implements the scanner and parser. Are they handwritten or generated using tools like Lex or Yank? Mm, .l file or .y files usually implied later. Okay. Just in time compilation tends to be the fastest way to implement dynamically typed language, but not all of them use it. What
Yeah.
reason are there to not just in time?
Mm-hmm.
Okay.
So now use JIT.
Yeah, it's not use JIT. Most LIMS implementation that compile to C also contain an interpreter that lets them execute Lisp code on the fly as well. Why?
There was
Okay.
one time I wrote Lisp with Rochan. That day he was showing me how to write a Python compiler, and he wrote it in Lisp. It was very nice. Lisp is a very fun language to use to
Mhm.
if you haven't tried to like learn any advanced concepts like programming wise or maybe programming language wise rather. Lisp is a very fun language to look at stuff.
Makes sense. So let's see how can we go over these challenges? So open source language, what language do you think we should?
Right now,
Yeah, can we do it now? Or do you want us to?
I think next week is great. Honestly, we can like go through these questions. We can answer the other two questions, but like poking around our language might be like a stretch. Um, and I have to like run even. So um, so just thought
I think
compilation tends to be the fastest way to dynamically implement dynamic type languages, but not all of them use it. So they said they're asking why, which
mhm.
is a fun question. So what do you think?
I mean, from uh, I really don't see because like the way this JIT was explained, the just in time compilation,
That is
it
complex.
make it,
Nine
yeah, no,
parts.
not even complex. I think it makes it even for like dynamically typed languages, it make it easier for them. I mean, easier to compile them because like they already have like all the types and everything pre-written somewhere. So, but the reason not to use it, uh, I don't know. The reason not to use it might be because of like the complexity that is involved. I mean, around building just in time. I don't know. I'm just guessing though, but like, I mean, it's a bit complex compared to the other ones. But
And they
I
said it
think
takes time to
very
shop.
realistic.
And there's security reasons too.
Oh yeah, it takes time also. Yeah.
So for Lisp, for the other challenge, they talked about like using Lisp. And for what I saw online, Lisp actually has like some like an eval function or something that executes code at runtime. But other than that, Lisp is this is like a REPL, so like read eval print loop. Um, so having an interpreter sort of like allows it to take any code you write into it, and it can just like give a response instantly and stuff
Yeah.
though. And yeah, according to what I'm saying, it has a macro system and code as data philosophy, which means programs often generate and execute new code as runtime. So that makes sense.
Mm-hmm. Yeah.
So yeah, that's pretty much it. For the other one, we
But I
can
mean,
like poke around any programming language, I guess, and just like look through
yeah.
stuff.
I mean, most of this stuff are like new information I'm just saying. So, um,
Yeah,
yeah,
yeah, it's
I
very
like
refreshing. I learned a
the fact
lot,
that
like
I like the fact
like
that we
1 hour
had
or
to
so.
go through this. Because imagine if you had just jumped straight into like implementation, like straight to before, and then we'll now be seeing terms like libs, jits, and all the likes, and then we'll be like, oh, where is this
That's
even coming from?
yeah, definitely not it, because it's like we actually need to like get all this like background information to build off of.
Yeah,
Else we're just like
yeah.
wasting time
And then we'll be using this as even references going forward, like
going forward. Yeah,
good references.
I mean
But
we will not use every stream to build this, but like we may be circling back to it from stream to stream, like maybe over the course of the episode, the series rather. So like maybe continue building it and stuff. But I'm glad they're using Rust, so it's kind of like a win-win. So like you build Rust and you're sort of like are building your own compiler as well.
yeah, it makes sense.
So yeah, I think we should wrap up here honestly, because I have to run right now, and this place is a cafe, so I can't talk for that long. Um,
Yeah.
I'll disturbing others. So
So
so uh, I guess that's it from me. Thank you so much everyone for coming to watch. We appreciate your support in the comments and the chat. Um,
yeah,
yeah. So
I have a
from my end,
few. Yeah,
catch you same place next time, next week. Emmanuel,
yeah. So yeah, I wanted to point out that we also had like interactions in the comments.
in the
I
comments.
see
Yeah, very nice. Yeah,
it's Sam, I am you. Thanks for showing up. I also see Joseph, Logical. Thanks for showing up. And yeah, no gamer. Hi, Quinoma. Thank you for stopping by.
thank you,
Um,
General
yeah, Joshua also stopped by from LinkedIn, and we had
Gregory
Gregor, and we
and
have
Oluwafemi.
Fumike. Thanks, guys.
Thank you for coming by.
Yeah. So I guess that wraps up this episode. But I mean, and a lot to digest. I still even have to like go over these chapters and like some of the links that are there and try to do some lookups because most of these stuffs uh, are like stuff that I'm just getting to know about and hearing about for the first time. So
Yeah,
it's actually fun and awesome. And these are like concepts that most times developers or software engineers uh, just don't. I mean, just don't like delve into. I mean, it's not like they are not. It's not like they are not essential or they don't want to. But most times, some developers don't even know about it to start with
yeah.
because of like abstractions and things that we have now. But
Abstractions are great, but you need to be at a certain level, um, engineering wise, to start using abstractions, or else you just not understand so many things.
yeah, so it's just good that we're touching things like this though. And myself, I'm getting to learn a lot. Chinedu also stopped by. Well, Chinedu is asking
Thank you so much,
for
Chinedu.
yeah, thanks, Chinedu. He's
Yeah,
asking for
definitely,
yeah, we'll be using our
most
script.
definitely.
Yeah,
It says I've read that book and done some of the concepts too. It's an amazing book, rooting for you guys big time. Thank you, Chief.
oh, thanks, Chinedu. So we're not just the only nets, the only at least you've seen somebody that's done what we are trying.
Yeah,
That's
Chinedu actually told me. He told me when he was reading a compiler. I think he got to like the front end. He built the front end parts out. I'm not sure how
oh,
far he has gotten now, but when he finished, like when he was on the front end or was about to finish or something, he told me about it. He was using Rust then.
oh,
Yeah,
no,
yeah, really
thanks,
nice
Chinedu.
work.
Thanks for the support. Thanks, boss. So we hope we get to yeah, we hope to get to do something meaningful
And
with
Chinedu is
this.
streaming now
But
too.
yeah,
He streams now too, so
it's been
we can
good.
like bring him on. Oh, it's like my pin too. Yeah, for sure.
Oh,
Check it out.
okay. That's actually a nice idea. We could you could do like a joint stream with him.
Yeah,
If
we could bring him
you're
on.
interested.
Yeah, maybe
Yeah.
next week when we start, we can just bring him on and be like, let's stream together, something like that.
Mm, yeah.
Yeah.
Awesome. Awesome.
Okay. All
Uh,
right.
yeah. Thanks, guys. Yeah. 2 hours already.
Yeah.
We appreciate the support and yeah. Um, this is like a okay. I'm actually done with my stream though.
Definitely next week. We'll bring you on next week, Chief. Wait, let's
Next
do the stream together. Let's do that proper. We'll promote it and like build the stuff live. I think Chinedu will be like a great mentor to have on the stream because I have no idea what I'm doing honestly. But I mean, the idea is to learn it anyways.
exactly.
So
No give.
yeah.
No why saying bring me on too. Don't worry, we'll bring everybody along. Everybody, everyone will be invited. um,
All right.
yeah,
Okay, bye everyone.
yeah,
Signing out.
yeah. Thanks, guys.
Yeah.
Oh.
Let me stream now. Bye.